Now that we have our power supply, we're going to start looking at circuits and start building some circuits. Initially, what we're going to do is we're going to do design. We're going to be doing, let me pick up the pen. There we go. We're going to be designing logic gates or using logic gates in our design. In other words, we're going to look at digital circuits. And digital circuits are circuits that have digital inputs and have digital outputs. By digital, we mean that the input and output values of these circuits are defined either as a 0 or as a 1. So they only have two states that are useful. Now, indeed, the circuits are working on potentials. So this is in volts. So they have so at any one time, the input may be, let's say, between 0 volts and let's say 5 volts. And any one time, any output is close to 0 and close to 5. So the way these circuits work are the following. There are two thresholds that are set. One is a threshold for what is a 0, and the other one's a threshold for what is a 1. So in this particular case, if we have a signal, an input or an output that's at 0 volts right here, we call that a 0. So in this region, as indicated by this 0, all of the input or the outputs are 0. Yet as it exceeds this 0 threshold here, then we go into kind of a undefined state, and many times that is indicated by an X. And so during this undefined region, where the potential is between the 0 threshold and the 1 threshold, the operation of the logic gate is unknown, or it's undefined. Once we exceed the 1 threshold up here, which is typically, depending on the logic family, maybe something like 3 volts, is that now the logic family interprets this as a 1. So this is a 1, which is indicated by this area here. And then once it exceeds the maximum potential, then you get into the danger land. Okay, so in this case, you can actually damage the circuit. So we continue our progression, even though the potential is dropping in this region. During this entire region, it is still considered a 1, interpreted as a 1. Once we drop below the threshold, we go through very quickly. We can go through this undefined zone, and then even though we're bouncing around here, we're still interpreted as a 0. We come back up here. Now all of a sudden we say that we are back to a 1. So we are taking a analog voltage, in other words, a continuous voltage, and we're basically discretizing it into either being a 0 or a 1. So that's kind of the digital circuits in a nutshell. Now, how do we deal with functions? Okay, because now we define digital circuits, it'd be nice to understand is to make things out of them. And so we do it by something that's called a truth table. And so a truth table defines the inputs of a logic function and the output of a logic function. And remember, the inputs can only be of values of 0s and 1s, and the outputs can be also values only 0s and 1. So here's a very simple truth table. If the input is a 0, the output is a 1. If the input is a 1, the output is a 0. Well, truth tables become kind of awkward, so we can write this as a Boolean logic expression by saying the output is equal to the inverse, this over bar here, the inverse of the input. And so we can also symbolically represent this as the input going through this triangle with this little circle on the end of it, produces an output, and we give it the name, this is an inverter function. Now we can have functions that have two inputs. So this is a function, a logic function that has an input A and an input B, and it produces a single output C. And so we say that, so what does it say here? It says the only time C is going to be a 1 is when both A and B are 1s. So what this is, so we can write this symbolically as C is equal to some function of A and B, and we use the little circle here to say that that function is an AND function. We can do this as represented by a logic gate where we have input A, input B, and it produces an output C. And notice we continue to use that little circle here in this logic gate, and this is called an AND function. So we say C is equal to A and B. By the way, we could say C is equal to A and B and D, for example. So you can have you can have more than two input AND gates. And then next example is something called a half adder. And in this case, you have two inputs, as indicated here, and two outputs. This is the sum, and this is the carry to the next output. And so this would look something like this. A and B are the inputs, S and C are the outputs. This is the truth table for it, and we find that one way of writing just the output S, you can try to write the output C yourself. So what do you think C is? You should discover it's an AND function. And you can say S is equal to inverse of A and B, or A and inverse of B. So these are just some tables that describe how we can get logic functions. Now let's look at some examples. The first example I think we've already talked, well, we haven't talked about, we talked about the AND, but now we're going to talk about an OR. This is the truth table of this, which says 1 is, or output is 1 in any time either of the inputs is 1. And so this is the output. C is equal A or B, and C is equal to A or B. This is written symbolically by this OR symbol. Notice we use the plus sign here. Many times, because of the fact that we have this kind of slopey front on the front of this, is that we could ignore the AND signal, but I think I'll keep the AND signal here, or the plus signal here, plus symbol, I'm sorry. And then this obviously has to have a power supply associated with it. Many times we drop the power supply and just say the logic circuit looks like this. So this is a logic circuit for C is equal to A or B, and we find the relation, the rule for doing that is done through the truth table. Okay, so what would a real two-input OR gate look like? Well, it turns out we've already had this kind of level of abstraction here. So we talked about C is equal to A or B. We said that's a truth table. We said here is the symbol for the logic gate. And this is actually what you would buy, an example of what you would buy if you were to purchase one of these. It has an input A, an input B, and I just covered up the output C, but it's this little wire here. And it says what? It has about 7 transistors, it has a bunch of diodes and a bunch of resistors. And I believe this is a logic family that's called TTL. Okay, and so there are many different logic families, and so yeah, that is TTL because it's that part name. But you don't have to worry about this. Okay, so as far as you're concerned as a logic designer, you just purchase this. So this becomes a black box, and what you do is you totally focus on this particular side. Okay, so look at a two-input NOR circuit. A two-input NOR circuit looks a little bit like an OR, because an OR would have had a 0, 0, 0, 1. A NOR has a not OR, so the 0 becomes a 1. Let's see, this would become, I'm sorry, this is a OR. This is a 1, and this is a 1. So the 0 output, when we have 0, 0 for input, becomes a 1. the 1 output when we have 0, 1 for input becomes a 0, and so on. So we would write this in using Boolean algebra as the output is equal to the input, or the input A or input B, and we put the overbar on it. It reads C is not A or B. We would write this as basically it looks like an OR gate with a little circle on the end of it to determine the output. So now we can do something that's a little bit harder, and let's find a circuit that does this particular function. So we have a function here. This is a Boolean function, or a truth table that describes a logic function, and we want to see what symbols or what gates we need to make this happen. Well, this looks a little bit like an AND gate because it only has one out, so only one time do we get a 1 for the output. And so if we were to change this, instead of having B, let's say we had not B. So let's change this to not B. This would be a 1. This would be a 0. This would be a 1. This would be a 0. So if we said A and not B, we would have actually this, because 0 and 1 is 0. 0 and 0, of course, is 0. 1 and 1 is now 1, and 1 and 0 is 0. So what we need to do is, before we actually put B into an AND gate, what we need to do is we need to invert it. So convince yourself that if we put A and B into this circuit, we would get, let me just erase this so you can see it, we would get C according to this function. So this is a case of two logic gates that are put in a circuit to produce a kind of a custom function. Okay, so we can go the other way. Is we have a circuit that has, let's see, it looks like it has 4 different logic functions, gates, and we have an OR here, we have an AND, we have an inverter, and another AND. Go through and try various values of 0 and 1 in the inputs. Run through here. Let's see, if we put a 0 here, we would put a 0 here, we'd put a 0 here. That has to be a 0. If we have zeros into this AND gate, this is equal to a 0. This would make this a 1. That means we have a 0 here and a 1 here. This is an AND gate, so the output would be 0. So what you can do is we just confirmed this line. Now we could confirm the next line by just repeating that with A as a 0 and B as a 1, and try it again. Okay, so we can actually get some more involved. This is actually the gate we saw before. Okay, it looks like this. And then there's actually a name for this, and this is called an exclusive OR. And why would somebody come up with a name like this? Because it's useful. Is over time people found that they keep on building this gate, and then we will define it, and it looks a little bit like an OR, but it has this extra little arc to it. Okay, and we use the symbol of a OR, and then we make it exclusive by putting a circle around it. So this is how different gates or different functions are developed. Okay, and so we can do other combinations of gates. This combination of gate is a AND followed by an inverter. Okay, and so as we indicated before, this is what the AND function would look like. And then because we put a not, and this would be A dot B not, because the inverter. So this is what C would be. And it looks like the inverse of what an AND gate would be, which you would think so. This is so common that it is given a name of NAND, not AND, and it's given the symbol indicated here, which looks like an AND gate with a little circle on the end of it. And so in general, we find that these little small circles are a quick way symbolically to indicate inversion. So in this case, this looks like an OR gate, but we put a little circle in front of it. And what does that mean? Before we apply A to the OR function, we're going to invert it. So this is identical to having this inverter outside of the OR gate. And the function with the truth table would look something like this. So before we apply A to the OR gate, we are going to go through and we're going to invert it. Okay, and finally we're going to take a look at something that's a little bit bizarre, but I think it may be useful, and we're going to use it later on, is that this is an OR function. Suppose what we do is we invert everything. We invert the two inputs and we convert the two outputs. And instead of having the single output, so see all the circles here, and we are going to use an AND here. Okay, an AND function. So what we do is we look at this, and this is the original truth table, and this is the truth table of inverted inputs and ANDing them, and then taking the inverse of the result. And guess what? If you look at this column, these columns to this, and compare it to this column to that, you find you get the identical relationship. And this is a consequence of something called De Morgan's law. De Morgan's law says that basically we can go from an OR function to an AND function by clever use of inversion. And so the Boolean algebra statement on this is our OR function. This is all we do is we invert the whole thing, because if this holds, then the inverse must hold. Now we use De Morgan's law. Okay, we took the not A plus B and we just said it's A not B, and there's an and now before it was a plus. And then we would invert it again, and then we would get the result we had here. Now, is this important for you? Probably not, but I just wanted to expose you to the fact that in Boolean algebra, there are many different rules, and there are ways that we can cleverly convert one problem to another problem, just like algebra. And so before we actually start building this stuff, I would like to go through, we need to change the power supply. And so we're going to change the power supply actually by making it simpler. So before we had a Zener diode and a pass transistor for the voltage regulator. Now we're going to buy a voltage regulator in one package. So the voltage regulator is here, okay, and all it says is it has one terminal for the 20 volts in our case, and then it'll have one terminal, and we're going to have a 5-volt regulator. So 5 volts out here, and then of course you have to attach everything to ground. So the voltage regulator would replace all the transistor, the resistor, and the Zener diode in one situation here, one package here, which is kind of cool. Now let's go through and keep the LED in place, and you'll probably have to change the resistor here to keep the LED at the right operating current. So this is the device we're using, and this is it's called a 7805. It has an output potential, output voltage of 5 volts, plus or minus about 5%. It has a maximum output current of 1.5 amps, and the input voltage goes up to 25 volts. The picture of this is really, really important. One side's the input, one side's the output, and the center is the common. And you can tell by this tab, when you see the tab as a little recess here, this is the proper orientation. And flipping this thing around will cause you to damage it. So be careful with it. Okay, so we're going to test some logic gates just to see if we understand how to wire these things up and how to use them. And so the first one we're going to check is something called a NOR. This is a not OR, and this specific device is a 4001, and this is a CMOS device. And I use CMOS because it is generally less susceptible to people damaging it. So we get four of these in a 14 pin package. So see the pins, pin 1, 2, etc. up to pin 14. So the trick here is to connect it correctly so it works. The first thing to note is we will connect a 5 volt power supply to pin 14. We will ground pin 7. So that's a 0 on there. Then we will pick one of these gates to experiment with, and I just simply looked at the gate whose inputs are 1 and 2, and output is 3. So what I'm going to do is I'm going to hook its output to a current limiting resistor and then to a LED, so I can see if this output is at +5 or near +5 or near 0, whether it's a 1 or a 0. Then I'm going to get some inputs, and the way I get an input is I use a resistor, and it's just a few thousand ohms. It's not particularly important. And I bring one side of it to +5 and the other side of it to a switch. And then I take this point and I run it over to here. Now what happens here? When the switch is open, in this case, we have a path that is between +5 through the resistor and into the logic gate. So this would be a 1 in that case. Now, if I close the switch by pressing it, now what happens is that this side now becomes ground because I'm dropping the full 5 volts across the 2K ohm resistor. So then we can go through, and when we press the switch, we get a 0 here. We need 2 of them because we have 2 inputs, so we have one of them. Let me do this. So we have one of them right here. One button controls one input and the other button controls the other input. So you can simply go through and press the buttons, and you can build a truth table by watching the LED. And so the final one is I'd like you to test the truth table, determine the truth table for an exclusive OR circuit. And the exclusive OR circuit has the same pinout as the NOR. So we have +5 volts up here in pin 14. We have ground here. And then we can pick any of these to test. You might as well put this one on a switch, this one on a switch, and then we'll put this through a diode, and we'll be able to test the truth table on this. So this is one of your assignments, is to check. So you're supposed to get the truth table, for the NOR. Let me get my NOR. I'm interfering with Windows now. Hang on. Okay, and then the XOR, the exclusive OR. And this is a 4070 part. And this is the circuit that I built, and it's kind of sloppy. You can do better than this. So let's go through it and see if it makes sense. Over here is our power supply. And you probably want to leave it as is. You may want to clean it up a little bit. So that's a power supply here. Here is the 4001. Okay, this is your part. And these are your switches. Here's a switch here, and here's a switch here. These are the current limiting resistors that are put on the switch. So right over here is one of the inputs. So here's an input over here, and so that input comes up on this wire, and it goes down here. And by the way, I used the pins. 13, this would be 13, and then 12 and 11. So I use the other side of the package, but it makes no difference. I suggested that you use this side for your work. And so this is the other input here, and it goes over the other orange wire to here. And then the output goes up this white wire. It's kind of hard to see it. And then it goes through here, through the current limiting resistor, and then through the LED. And so you should be able to press these buttons and then determine, and then look at the LED to see if it works. So remember, with the LED, you don't necessarily know which direction it is, because the LEDs are not indicated in the package. So a suggestion I would always make is, when you try this at first, hook up the LED through here, and then hook it up into power, and just make sure the LED lights. Then you redo it from, you take that out, and then you go into the particular output you're looking for. The other thing is, I would check with either a voltmeter or a voltage probe. No, your differential voltage probe. By the way, this happens to be the probe of a voltmeter, to just make sure that your switches are running correctly. So measure this point and make sure it is switching between +5 and 0. So that's what you have to do, and I hope you have fun with it. This terminates our video and the conversation.